So last time, again, we were talking about equivalence relations. So back to the definition of equivalence relation. Quick recap. So a relation tilde on a set A is an equivalence relation, right? When it's reflexive, symmetric, transitive. X is always related to X for every X. X related to Y implies Y is related to X for every X and Y. And for every X, Y, and Z, X related to Y and Y related to Z implies X is related to Z. And, we had a couple examples. And then this example of partitions, right? So given a set A, you partition A into non-empty subsets when those subsets are disjoint, and the union is all of A. So exactly what the word means. And those subsets are called the blocks of the partition, and you define a relation on A by saying that two elements are related when they're in the same block. Right. So 3 is related to 4, 3 is not related to 2. 9 is not related to anyone other than 9. 7 is related to 6, but 6 is not related to 8, or 2, or 1, or 9. So on and so forth. And that's an equivalence relation. That's always an equivalence relation, this partitioning. And then the theorem, so we proved that's an equivalence relation. And then the theorem about equivalence relations, you can call it the fundamental theorem of equivalence relations if you like. If tilde is an equivalence relation on A, equivalence classes. Given an equivalence relation tilde on A, for each x in A, you let bracket x be the set of all y's in A, such that x is related to y. All right, so bracket x is all the things that x is related to. And that's called an equivalence class. And given an equivalence relation, the equivalence classes partition A. So partitions give you equivalence relations give you partitions. In other words, they're essentially the same thing, just spoken about in different ways. So we proved the theorem, and then there's this fact for next time. I kind of wanted you to prove that. Let tilde be an equivalence relation. Use the theorem above to prove that the following. So when y is an element of the equivalence class of x, then the equivalence class of y is equal to the equivalence class of x. So from last time, let's actually do that. Oops. So from last time, let tilde be an equivalence relation, okay, and use the theorem, the partitioning theorem, to prove that if y, an element of the equivalence class of x, means the equivalence class of x is equal to the equivalence class of y. Okay, proof. All right. Assume y is in of the equivalence class of x. Right. So by definition, what? What does that mean by definition, that y is in the equivalence class of x? It just means what? What does it mean?
X is related to Y.
X is related to y, right? By symmetry, we also get what? Have what?
Y is related to X.
Now, y is related to x, which means what is an element of what?
X is an element of Y.
X is an element of, bracket y, equivalence class of y, right? Okay, by reflexivity, right, x is related to x, so x is an element of the equivalence class of x. Therefore, the equivalence class of x intersect the equivalence class of y. X itself is an element of the equivalence class of x intersect the equivalence class of y. Right? But equivalence classes are either by the theorem on partitions, since equivalence classes partition A, it cannot be, we partition A, it must be that the equivalence class of x intersect the equivalence class of y is empty, or the equivalence class of x is equal to the equivalence class of y, right? But since x is in the equivalence class of x intersect the equivalence class of y, it's non-empty. It must be the latter of the two. So going with the former and latter construction, what does former and latter mean? When you present two things,
The former is the first case and the latter is the second case.
right? When presented with two things, the former thing is the first one. The latter thing is the second one. Very annoying use of the English language, but people do it. It must be the second possibility. It's a very 19th century thing. Former and the latter. But it persists into the 21st. If you ever, so once in a great while, I have to delve into some older types of mathematics, things that were written, well over 100 years ago. And if it's in English, I'm always, if it's in French or German, Russian, I just forget about it. But if it's in English, I'm always struck by how not funny, but how differently people used to write back then than they do now. All right. It's like they used funny words just to show off how educated they are or something. Given that, okay, given any equivalence relation that you might have, you you definitely would want to know what's the partitioning that it gives you. Now, here's another relation. Okay, now, I'm not saying it's an equivalence relation, but if you have a relation that makes a partition, okay, that makes equivalence classes a partition like this, then it has to be an equivalence relation, because partitions give you equivalence relations give you partitions. So here's another relation right here. Given n in this integers, and this is a really important one, by the way. Given n an integer with n at least 2, we say that x is equivalent to y modulo n, denoted this way, when y minus x is a multiple of n, that is, n divides y minus x. So recall that, when dividing an integer x by n, we obtain a quotient q and a remainder r between 0 and n minus 1. Right? Whenever you divide, and you don't want to use fractions, right? You just want to use whole numbers, you get a quotient and a remainder. So like 100 is quotient 33, remainder 1. So the following sets are a partition of the integers. Right? Everything that's got remainder 0, everything with remainder 1, everything with remainder 2, everything with remainder n minus 1. So that's a partitioning of the integers. So we'll do that right here. So let's show that. That x is equivalent to y modulo n. X is equivalent to y modulo, I'm going to leave out the n, mod n. If and only if x and y have the same remainder, when divided by n. Right? X and y have the same, are equivalent modulo n if and only if they have the same remainder. So remember, an if and only if proof has two directions. So let's assume x and y have the same remainder when divided by n. Both have remainder r in 0 to n minus 1 when divided by n. Okay, that is, right, x is equal to n times k plus r, and y is equal to n times l plus r. Right? X is a multiple of k plus that remainder. Y is a multiple of k plus that remainder. Therefore, y minus x is equal to nk plus r minus nl minus r, which is equal to, so the r's cancel, right? N times k minus l, which is a multiple of n. Meaning what? So y minus x is a multiple of n, which means what? Hello? Are you there? Okay. Y minus x is a multiple of n. It's n times k minus l. That means what? As far as equivalence modulo n. What was the definition of equivalence modulo n?
Y minus x is a multiple of n.
Yeah, or n divides y minus x, whichever direction you like to say it. Right. So this means that x is equivalent modulo n to y. And let me stick with that notation. Do it that way. X is equivalent mod n to y. So x is equivalent mod n to y if and only if x and y have the same remainder when divided by n. So we're proving that, right? And we have to prove two directions. So first we did the backward direction. Suppose x and y have the same remainder when divided by n. Now let's do the forward direction, but let's do it by contrapositive. This is my favorite way to do it. All right, so by contrapositive, we're not using contrapositive. All right, assume x and y don't have the same remainder. Well, don't have the same remainder. When divided by n. Right, say that x is equal to n times k plus rx, and y is equal to n times l plus ry, where rx is not equal to ry, and rx and ry are in that set of possible remainders. Okay, since they're not equal, one is smaller than the other. Since they're not equal, one is smaller than the other. Either Rx is less than Ry, or Ry is less than Rx. Alright, so if Rx is less than Ry, then y minus x is equal to nk plus r, or nl plus r. Oh, did I do that wrong upstairs? L minus k. That's an L. That's the k. L minus k. nl plus ry minus nk plus rx, right, which is equal to n times L minus k plus ry minus rx, where ry minus rx is an element of what? So ry and rx, these two remainders are unequal, but y is bigger than x. So where do ry and rx land? Rx and ry are both in this set, right? But they're unequal. So their difference is not 0. The difference is not 0, right? And the difference is less than n minus 1, or less than or equal to n minus 1. Right, so the remainder of y minus x when divided by n is not, the remainder of y minus x when divided by n is not 0. Is not 0. So x is not equivalent mod n to y. That's if Ry is bigger than Rx, or Rx is less than Ry. If Rx is bigger than Ry, could be that, then again, y minus x is equal to nl minus k plus ry minus rx. But this time ry is the smaller one, but they're still unequal. So this time, where's ry minus rx? Right, so ry is smaller than rx, but they're unequal, so it's not 0. So this time the difference isn't positive, it's negative. So it just puts it in here. Therefore, y minus x is equal to n times L minus k minus 1. So I subtract an n from this, and I'll add it to that, plus n plus ry minus rx, where n minus, or n plus ry minus rx is an element of this set, adding n to it. So, like if you add n to negative 1, you get n minus 1. And if you add n to this, you get positive 1. Right? So that's the remainder. So the remainder of y minus x when divided by n is not 0. So y is not, or x is not equivalent to y mod n. And that's the end of that proof. It's a little bit more than maybe that's more involved than a lot of proofs that I would ask you about in here. But what we have just shown, right, is that this relation x related to y modulo n gives you these equivalence classes. Well, sorry, the relation defines this partition. So since the relation defines this partition, right, where two things are related when they're in the same block of the partition, it must be an equivalence relation, because those are the equivalence classes. All right. So the equivalence classes. So the relation defines the above partition, and so the relation is an equivalence relation. With these equivalence classes. So this is the equivalence class of 0, 1, 2, up to n minus 1, because those are those remainders. So this is the equivalence class of 0. This is the equivalence class of 1, equivalence class of 2, all the way down to the equivalence class of n minus 1, which is equal to the equivalence class of n the equivalence class of minus 3n, so on and so forth. This is the equivalence class of n plus 1, the equivalence class of 7n plus 1, so on and so forth. Right? 1 and n plus 1 have the same remainder when divided by n, therefore they're in the same equivalence class. So now what you can do with that is, now you can actually, so there's the story goes much deeper now. So now you can actually define multiplication and addition using these equivalence classes. So for example, like 3 times 4 modulo 6, so modulo 6, 3 times 4 is 12. But 12 is a multiple of 6, so that's equivalent to 0, mod 6. But that's what you'll do in modern algebra. And, you know, if you're taking computer science, you would do some of that as well. Okay, but we're not going to do that here. Although it's pretty cool. All right. So here's one to think about for next time. Some things to think about for next time. Okay, 1. Show that equivalence mod n is an equivalence relation directly. All right, that is, show that it is reflexive, symmetric, and transitive. So show it's an equivalence relation that way: reflexive, symmetric, transitive. You know, I mean, you don't have to think of what the equivalence classes are. You know, we've already done that, but you know, give a proof just directly from the definition of equivalence relation. We did it just by showing that the relation defines a partition, which is the less common way of doing it. 2, consider the following relation. So, not finite. Yeah, finite, sorry. Consider a finite set A. Define a relation twiddle on, not A, on the power set of A. What's the power set of A? It's the set of all subsets of A. I guess I shouldn't use the word X. It's the set of all subsets S. The set of all sets S, S is a subset of A. So define a relation on the power set of A by S is related to T when the order of the symmetric difference of S and T is even. What was the symmetric difference? Right. S symmetric difference T was equal to what? It's equal to S minus T union T minus S. All right, so everything in S union T, or you know, you can think of it as S union T minus S intersect T. So define a relation on the power set of A this way, via this symmetric difference. Don't show it's an equivalence relation. It is. Okay, this is an equivalence relation. What are the equivalence classes? Okay, showing it's an equivalence relation, whatchamacallit, the reflexivity and symmetry are easy to show. Transitivity is more involved. Well, it's not that hard, but it's just more involved. Okay, but don't worry about showing it's an equivalence relation. Just assume it is. Okay, but what are the equivalence classes? Okay, so like do an example. Like take a 3-element set, and build the power set, and then look at the equivalence classes. Right, and then see what they are, what those equivalence classes are. All right. So on to the second part of, third part, I guess, of the chapter. You know what? Why don't I start a new, instead of always making them one file? Partially, second part of the chapter, third, so partially ordered sets. So what I was saying before is that relations in and of themselves are not really that interesting because it's just any old subset of the Cartesian product of A. Which doesn't really have to be anything special. It can be something just, something kind of strange or something not strange, or there's just too much variation. It's when you start putting conditions on a relation that relations become interesting. And then the basic example is the equivalence relation. But partially ordered sets are another one, and they're really important, partially ordered sets. So definition. A relation, now nobody uses twiddles for partially ordered sets. This relation on a set A is called a partial ordering when, okay, this doesn't mean less than or equal to. It's a symbol that means something like less than or equal to. All right, but it doesn't necessarily mean that. Less than or equal to is only for numbers. Okay, but partially ordered sets aren't always on numbers. All right. So a relation less than or equal to, or this. So we say less than or equal to, but it's not that. It doesn't have to be that. It could be that. This on a set A is called a partial ordering when sigma is reflexive. So again, you have reflexivity. For every x in A, x is less than or equal to x. Antisymmetric. For every x and y in A, x less than or equal to y and y less than or equal to x implies x equals y. And transitive. For every x, y, and z in A, x less than or equal to y and y less than or equal to z implies x is less than or equal to z. Okay, so a partial order is reflexive, antisymmetric, and transitive. Antisymmetric in the sense x less than y, x less than or equal to y does not imply y is less than x. X less than y does not imply y is less than x. If you did happen to have x is less than y and y is less than x, that's only the case because x and y are the same. Right, and the set is reflexive. All right, so it's kind of like equivalence relations, except in that it's reflexive and transitive, but it's completely not symmetric, and that gives you a whole new category of things. I mean, it's just very different than what an equivalence relation is. No partitionings, anything. So, for example, so note, or another definition. So if this is a partial order on A, and x, y are in A, and either x is less than or equal to y, or y is less than or equal to x, then x and y are said to be comparable. So not the English, not the English language. What does comparable mean in the English language? So if I go to the store to get tires and I say, I want these Firestone tires for my car, and the guy's like, well, we don't have those, but I got these Michelins which are comparable. That means what?
They're like similar.
Yeah, they're similar to each other, right? Here, it's not that. It's comparable. They can be compared. Okay, so you can compare x and y. X is less than y, or y is less than x, but it doesn't have to be the case in a partially ordered set. That's why it's called a partial order. Right? It's because some things in them are not comparable, or not comparable. So spelled the same, but maybe say it differently, like comparable. So the best example of a partially ordered set is this. So let A be any set. And then this relation, the subset relation, with its usual meaning, is a partial order on the power set of A. So, for example, we'll say A is equal to 1, 2, 3. Now let's do x, y, z. X, y, z. Right? And here's that partial order. We have subset of order 3, subsets of order 2, x and y and z, x and z, and then subsets of order 1, z, x, y, and then you've got the empty set. So the empty set is a subset of all of these guys. All right. The set containing z is a subset of these two. The set containing y is a subset of these two, and the set containing x is a subset of these two. And then all of these are subsets of x, y, z. Right? So, like y, the set containing y is a subset of the set containing x, y, and z. However, like any two subsets of order...
Did you stop presenting?
I'm sorry, what was that?
I'm sorry, I said, did you stop presenting?
Oh, did my screen sharing go away?
At least on mine, I just want to make sure no one else is having a
you're
problem.
right,
If it was
it did.
just me, I'll leave.
Sometimes my hand, I guess, it touches that thing. Can you all see the screen now? How about
Yeah, it's better now.
okay? All right. And y, z are not comparable. So this diagram is called a Hasse diagram. And that's called a Hasse diagram. And that's a partial order. One doesn't have to really prove it because we know all this stuff. It's just by definition. Right? The proof is simply by definition, except for transitivity. Yeah, I guess let's give a proof. Let's give a proof. Well, we did that proof already. So here. So reflexive, and this is by definition of the subset ordering, antisymmetric. Again, it's by definition of the subset ordering. And transitivity, we proved this a while ago. So we proved a while ago that X subset Y, capital Y, and Y subset of Z implies X is a subset of, or you did it in your homework. Now, by the way, let's take a look at the next assignment. Which is due on, whoops. Oh, don't tell me I didn't post it. Oh, here it is. No, that's the solution. Sorry.
You forgot to update the notes from last time.
Did I forget to? Did you hit I thought I did. Did you hit refresh when you went to the...
Yeah, I kept hitting it.
Huh.
Because I wanted to work on that for next
Apologize.
time.
If I do that, make sure you just, email me and let me know.
Shoot you an email.
Yeah, no, you're right. I did. It's not there. Okay. Well, it'll be updated today. So let's look at number 5. This is an interesting one. Or number 3, sorry. Given A and B in the set of natural numbers, we write A, like, vertical line B to mean that A divides B, or B is a multiple of A. So that's a standard notation there. So A, vertical line B, means is read as A divides B. That's a partial order on the set of natural numbers, right? Like 3 divides 6 and 6 divides 24, therefore 3 divides 24. But it's anti-symmetric. If A divides B and B divides A, then A and B actually have to be equal. You got to actually give a proof of that, okay? But it's not hard. And then, of course, any number divides itself. We've known that since 2nd grade. So that's a partial order, but it's not a total ordering because some things aren't comparable, right? 5 neither 5 divides 7 or 7 divides 5. So that's a classical partially ordered set. It's got a lot richer structure than the one we just talked about here. This subset ordering. So this diagram is a Hasse diagram of the 3 subset, the 3-element set subset ordering. So like Y is a subset of X, Y, Z, X and Y is a subset of X, Y, Z, so on and so forth. And then the sets X, Y, and Y, Z, they're not comparable. Neither is one a subset of the other, or the other way around. And of course, the empty set is a subset of any other set, including itself. And so that's a classical partial ordering. But then again, there are total orderings, that you're used to when you just talk about the classical meaning of this symbol. So that symbol is used for partially ordered sets in the abstract, this less than or equal to symbol. So here we use the subset symbol, which of course is, a similar idea than the less than or equal to symbol. It's a related idea. On the homework, we have this vertical line on number 3. A vertical line B to mean A divides B. That's a partial order with a totally different, type of symbol. But when you talk about partially ordered sets in the abstract, you always use this symbol, which doesn't necessarily have the classic meaning. But let's look at the classic meaning. All right, the set of all real numbers R is a partially ordered set. Under the usual meaning of this symbol. In fact, this is called a totally ordered set. Instead of partially ordered, because every pair of elements is comparable. Okay, so the usual meaning of that less than or equal to symbol, it gives you a partial order or a total order. But you can use it in different ways to make new kinds of orderings. So here's an example. So the usual meaning of this on, let's just do the integers, is of course, again, a total ordering. Okay, so now define a new relation. I'm using the exact same symbol. Okay, I'm going to use the exact same symbol, but it means something totally different now. So, as students of mathematics, this might be a new idea to you. Okay, but, people who are, well-versed in, not necessarily well-versed, but who have started to learn how to, to do coding, computer programming or whatnot, that the same symbol has different meanings, when you compare different data types. Right? And you can't compare different data types with the same symbol. Right? If you say, if you compared a number and a letter, what language do they teach nowadays at Wright State? Java? They still do Java or Python, or what is it?
I'm using Python.
Python, okay. In Python, right? You get these lists, right? And you ask it, is it equal to 7? What's it going to do? It's gonna say, well, you can't compare these things. They're totally different. right? It's gonna object, right? This is the way that you put a double equal or something like that, right? So anyway, this, okay, has the usual meaning on the set of integers. So if I said this, that means I'm comparing two integers, x and y. Okay, and I'm comparing them in the usual way. 3 is less than 5. Great. 3 is not less than 2. Great. Okay. 3 is less than or equal to 3. So we're all up to speed on that. Now I'm going to define a new relation with the same symbol on a different data type. So then I define a new relation less than or equal to on z cross z by defining, so two elements, A and B, when, so AB is less than or equal to CD when, now there's different ways. Come on. AB is less than or equal to CD when A is less than or equal to, let me not use CD, let's say XY. When A is less than or equal to X and B is less than or equal to Y. So this is the new meaning on Z cross Z. And these here are the usual meanings on just Z itself. Does everyone see what I'm getting at here? So, for example, or I guess I can't. Let's do it this. For example, 3 comma 12 is less than or equal to 13 because, let's put a 3 there as well. 13 because 3 is less than or equal to 3 and 12 is less than or equal to 13. So these two elements satisfy the relation because in the usual meaning on Z, 3 is less than or equal to 3 and 12 is less than or equal to 13. But 312 is not less than or equal to, what shall we say, 4, 2, because 12 is not less than or equal to 2. So some pairs of integers are not comparable. So it's no longer a total ordering. Okay, we want to show that it's going to be a partial ordering. We want to show that it satisfies the definition of a partially ordered set. So, well, we got to go. So why don't you do this for next time, okay? So for next time, show this as a partial order on Z cross Z. On Z cross Z. Okay? All right. Have a good day, everybody, and I will see you on Friday. Email me with any
I have a
questions or
question.
concerns.
Will we be allowed a sheet like on the first exam?
Yeah. Okay?
Thank you.
We'll talk more on Friday. Okay. All right, guys. Have a good day.